Okay, we're recording. Okay, so last time we were talking about polar coordinates. We're going to continue on with that. We'll talk about how to understand equations in polar coordinates. Let's start with this equation right here, r equals 3. Now, from a geometric standpoint, this is actually pretty easy to understand. After all, minus signs aside, that just says the distance from the origin has to be 3, which says we're looking at all the points where this distance is 3, and of course that's going to make a circle. Right, so geometrically that's pretty satisfying. But supposing you hadn't noticed that, or said differently, how does the algebraic process lead to the same conclusion? Notice what you can do. Real clever idea. Just square both sides of that equation. And having done that, recall we already know that r squared is x squared plus y squared. And so lo and behold, we find ourselves with the rectangular equation, and now no geometric intuition necessary. We already know that that's the equation of a circle centered at the origin, just from high school algebra experience. Okay, so good to be able to do this both different ways, but we're going to see a lot of converting algebraically from one to the other. Okay, let's see here. Different trick for this one. Now again, theta gives us an angle which gives us a direction, and points that are in that direction, not too hard to see, that gives us half of a line anyway, and then you remember r is allowed to be negative, so that gives us this whole line. So easy geometric argument again. But again, what if I didn't notice that? How would I see this algebraically? Different trick. Take the tangent of both sides of the equation. Then we find ourselves looking at tan theta, which we again have a pat established formula is y over x. And again, then we end up with something that's rectangularly familiar, and we know already is the equation of a line. Okay. All right. Now I'm going to skip over this next example momentarily and come back to it. I just want to do one more where we play algebra games. R equals cosine theta. There is a different trick here. This is, every one of these is different. In this case, now you're going to see the r. You're going to notice that it's nice to connect r squared to x squared plus y squared. You're then going to have this strong temptation to square both sides of the equation. And that's not a good choice. Because if you choose to square both sides of the equation, then the right side would turn into cosine squared, and what do you do with that? How do you write cosine squared in rectangular coordinates? We don't have anything to do with that. Right? So here's the different approach. And again, this is just the trick that just happens to work in this case. Instead of squaring both sides, just multiply both sides by r. And then you get what you want in both sides. The left turns into x squared plus y squared, and the right turns into exactly x. Well, different example, different little clever trick. So just things to keep in mind, right? Always be on the lookout for these various different kinds of tricks for making these transitions. Now, to finish up this example, you'll notice this is not exactly in our favorite format for recognizability. What is this thing? To get into the format that we want, you have to do a process called completing the square. And I imagine all of y'all have seen that way back when and have probably blown right past it and long since forgotten the details of how to do that. And that's okay. But it is something that you need to freshen up on because it's a really useful algebraic technique. The big idea in this case is that these three terms you can kind of move around like so. And by adding 1/4 to both sides of the equation, perfectly legal, very conveniently, this turns exactly into a perfect square, and we win. Right? That makes the equation turn into a form that I can recognize. This is conveniently understandable as a circle. So, if you're a little rusty on completing the square, Google it. There's a million resources out there. There's a nice trick, you might say, for how to figure out what it is that you want to add to both sides of the equation to complete the square. In this case, I just pulled it out of a hat, right? But it's important that you know how to do that magic trick yourself. Okay, now back up to this example that we temporarily skipped. If you try to play with the algebra to turn this into a rectangular equation, you will fail. Not going to work out. So what we're going to have to do is basically point plotting. And it's a little tedious. But if you kind of group angles together and kind of, in some sense, do a bunch of angles all at once, it's actually not so bad, really. So I'm going to start off by thinking about, okay, what happens in the first quadrant here? In other words, as theta goes from 0 to pi, 0 to pi over 2, right? Just moving through the first quadrant. What's the curve doing in that first quadrant? Okay, so here's the thing. Theta is not the only angle involved in this equation, and this is a easy source of confusion. So make sure not to accidentally step on this landmine. Notice that 2 theta, not theta. 2 theta is the argument of the sine function. 2 theta goes from 0 to pi. And that's what goes into the sine function. So if you want to know how much of a sine wave are we going to see over this green range of theta angles, we're looking at the 0 to pi part of a sine wave, because that's what's going in to the sine function. And that's something that's easy to understand. R, namely sine of the blue angle, right? For half of a period that this is, goes up to 1 and then back down to 0. So this is our little giveaway of, let's see, we out of chairs?
There's one more up there.
Yeah, why don't you can just grab that. I'm sorry that we're tight this section. So as we look at these different green angles here, as we start in that direction and then go, progressively through these directions, I'm going to follow this little chart that I've got here, my R's, my purple little distances here. We're going to start at 0, go up to 1, and then back down to 0. And that's going to trace out something kind of like that, and thus my actual equation here starts off looking about like that. Clean up my picture. There we go. Everybody happy? Okay, let's do the second quadrant, and then I'll leave the rest to y'all work out as a nice example. Practice exercise. So let's see here. Second quadrant, we're looking at these angles, which means theta is pi over 2 to pi, which means that, now keep in mind, I'm actually interested in what goes into the sine function, which is 2 theta, which therefore goes from pi to 2 pi, which covers the second half, if you will, of a sine wave. Right? And so the second half of a sine wave starts at 0, goes negative down to -1, and then makes its way back up to 0. Now, this is a little confusing. So as we look at these directions, starting from straight up, going to straight left, as we go in that direction, this is telling us how far backwards negative into the fourth quadrant the picture actually goes. Right? So, for example, you take like an angle kind of like that. In that direction, we'll be going backwards, and thus something like that. So, as I go through these angles, let's see here, starting at 0, going negative, getting more and more negative to -1, and then back slowly as the angle increases up to 0. And so while the curve started like this, as the angle goes through the second quadrant, the curve kind of appears to go into the fourth quadrant. And it's a little confusing because, again, you're like, wait a minute, but I thought we were in the second quadrant. Well, the angles are in the second quadrant. The resulting points, having negative r's, are over in the fourth. Everybody good? There's some stuff to think through there and to kind of digest, so take the time as needed. Don't forget this is all being recorded. You can listen to it later, et cetera, et cetera. Okay. So now just to complete the whole picture for you, so you know what you're going to be aiming for as you finish the rest of this, this curve is going to, it starts like that, it continues through like that, as we've discussed, then it goes over here like that, and then it goes over to here, and then connects back up to where it originally started. It's kind of a little four-leaf clover. Everybody happy? Okay, think through those last two quadrants. Nice exercise. Okay, moving along. Sometimes you're going to go, instead of polar to rectangular, sometimes you're going to do rectangular to polar. There's a bad news, good news thing here. The good news is the plugging in part is pretty immediate, right? I mean, so why? I don't have to do a bunch of clever manipulations to turn this into something I have a formula for. Y is just r sine theta. End of story. Plug it in. Proceed. Everything's fine, right? So in that sense, it's kind of easy. That said, you do have to kind of get lucky. Weird things happen if these don't cancel. Can be therefore hard to solve for r if you wanted to solve for r, unless you get lucky with the algebra. So that's kind of the downside. One other little comment: be on the lookout for convenient opportunities. Now you could plug in this y right here as r sine theta. I could have done that from the very beginning. But notice I didn't. Notice I delayed the plugging in. I went ahead and squared that out first. That saved me writing down a bunch of trig. And then, before I actually get into the plugging stuff in, I notice, hey, look at that. X squared plus y squared. Boom. Lucky break. We did find a convenience. That's already r squared. Now again, you can plug in x equals r cosine theta and y equals r sine theta and blah blah blah, Pythagorean identity, but you're just reproducing effort that's already been taken care of. So this is much easier to just notice. So be on the lookout for those little opportunities. Okay, real quick observation about these last two examples. Notice both of them are circles centered on an axis tangent to the other axis at the origin. How about that? You'll even notice that the polar equation's kind of reminiscent. Right? This is a tip-off of how things are going to work out in general. Like, so for example, if this had, instead of being r equals cosine theta, what if this had been r equals 3 cosine theta? You could probably guess it's just an extra factor of 3, and it's going to look something a lot like this, just kind of magnified. The center will be at 3 halves instead of 1 half. The radius will be 3 halves instead of 1 half. But other than that, highly analogous. So nice little fact to be on the lookout for. These circles, by the way, are going to be convenient for us in various instances. And so make sure to be aware that their equations are very convenient. Okay, moving along. Cylindrical coordinates. This is a lot like polar coordinates. In fact, given a point in space, the way we write down the cylindrical coordinates, the very first step is to take a projection down into the xy plane, and in the xy plane, theta are just like polar coordinates. Therefore, the relationship between x and y and r and theta are just like in polar coordinates because literally the first two cylindrical coordinates are the polar coordinates. That's nice. The third cylindrical coordinate is z. It's literally the rectangular z. So a lot of people, noticing how heavily dependent on polar coordinates this is, actually call this polar coordinates in space, or polar coordinates in 3 dimensions, or polar coordinates in R3, take your pick. And I would call that a reasonable label, but I think you'll eventually come around to what I like to point out is that it still takes more effort to say polar coordinates in R3 than it does to just say cylindrical coordinates, right? So I think you're eventually going to come around to the idea that this really makes more sense to call this cylindrical coordinates. So that's the name that we're going to go with. Okay, so why do we call it cylindrical coordinates? And this is easily noted. That very, very, very simple equation is a cylinder. Because after all, r just tells you the distance away from the z-axis, and the set of points, a given distance away from the z-axis, is a cylinder. So, thus the name, cylindrical coordinates. Everybody happy? Alrighty. Let's see here. Another quick example. Here's the equation of a sphere. Correction, that's the rectangular equation of a sphere. How would I write this in cylindrical coordinates? Notice that the equation right there, are, again, sort of standard pat relationship there, allows me to rewrite this equation. And this new equation, all of the variables are cylindrical variables. So this result of plugging in that equation is what we call the cylindrical equation for that sphere. Yeah?
What if r is 0?
What if what now?
What if r is 0?
If r is 0?
Yeah.
Okay. Did you mean the radius,
right,
or the coordinate r?
I mean the c. Like
Yeah, that's right. Okay, so if c is 0, in other words. Yeah, if c is 0, then it's not a sphere. So, I mean, technically I should say that, this equation with the understanding that c is positive is a sphere. Yeah, the whole question becomes kind of silly at that point. Yeah. Okay. Oh, yes.
Sorry. So C is the radius of the sphere.
Correct.
And then and R is like the distance from the origin, it's like some point of the sphere.
That's right. Exactly. So that is actually a point that I'm going to be getting to. Let me go ahead and do that since you already asked it. You have to be careful at this point with your use of R as a letter to describe things with. Now, in high school algebra, they're pretty comfortable just using R to mean a radius of something. If you have a circle in the question, circle of radius R, right? You can't do that anymore because R is now a variable. R means something, consistently in all these contexts. R is the cylindrical or polar, given the context, variable. Point is, it's a variable. So, for example, think about if you were doing a question in rectangular coordinates, would you ever describe a distance from this point to that point as being distance x? No. That'd be ridiculous, right? No, x is a variable. X tells me x is a coordinate, right? It's part of how we describe location. You can't use it to represent a constant that plays a different role in the question. So likewise, be careful. Don't use r as being a radius of some fixed thing because it's not a fixed value. It's a variable. Now, the easy workaround there, if you like, is just use capital R. Let me see if I can actually make a decent cap. There we go. So capital R, perfectly fine, no problem. And etc. You can use R tilde or R naught or whatever. Anything but R, lowercase r itself. Go crazy. It's all good. Okay. Right. Okay, so yeah, back up to this last example. There's a really neat observation to be made for this last example, and that is actually reminiscent of something we talked about back in 1.5. You remember we had this theorem that says that if you have a plane, if the equation of the plane doesn't have any y's in it, then the resulting plane is parallel to the y-axis. Okay, and why I like that theorem is easily observable algebraic observation gives significant, meaningful geometric punchline. Right? So something analogous is going to happen here. You're going to notice in this equation, this is a cylindrical equation in the sense that the variables z and r are both cylindrical variables, but then you're also going to notice no thetas. Right, now there's no theta axis for us to talk about being parallel to, so that we don't get the same conclusion. But there is a really powerful conclusion to be had here. And here it is. If you notice, let's ask the question, let me say, what happens if you look in this theta slice, this theta cross-section, fixed value of theta, all the points in this half plane at the same theta, right? What would the cross-section of our surface be, and how would that compare to the cross-section in that theta slice, or in, that theta slice, or this theta slice? Right? How do those slices differ from each other? Well, each one of these represents plugging in a different value of theta into this equation that has no thetas in it, and so nothing is different, right? Whichever theta slice you're looking at, all the cross sections look exactly the same. So what that tells us is this surface, whatever this surface is, yet to be determined, it has to be rotationally symmetric around the z-axis, because all those slices look the same. So, how are we going to understand a given one of these slices? Let me fix a value of theta. I'm going to start off by just picking one like this, for example, and thinking about that theta slice. In that theta slice, what does this equation mean? Well, z equals k times r is it's a part of a line coming out of the origin. So easy. And then what happens when I rotate that line around the z-axis? I get a cone. Boom. Everybody on board? Now, I just deliberately left out a little subtlety, just to let's get one in the win column first. Now, let me address, what happens if z is negative. Can z be negative? Is that okay? If z is negative, after all, let's see here. If z is negative, that would mean that r would have to be negative. Is r allowed to be negative? Yeah, totally. Not a problem. Right? So really, keep in mind when we're talking about a particular value of theta, we like to think of a particular value of theta as being a half plane, but it's actually perfectly okay with just negative values of r to go back to the other side. So really, when we were looking at this half plane hanging off of the z-axis, yeah, it's perfectly okay to go over to the other side. So the line, what I had drawn as being sort of half of a line there, is actually perfectly okay to be a whole line, and that then gives us this entire cone. Yeah.
And k is just like some kind of stretch factor on the arc.
It's just basically telling you the slope of this cross-section line. Yeah, totally. Is that cool?
Yeah.
Okay, so this is what we call a full cone, as opposed, what we typically think of like, ice cream cone, right? That's kind of half of a cone. Okay. All right. Nice example. The big punchline on this example isn't the cone. The big punchline on this example is this really valuable general observation that if your cylindrical equation has no thetas, then you have a rotational symmetry around the z-axis. Big win. Okay. Spherical coordinates. This is a little weirder. Let me walk you through what all these cylindrical variables do. Starting with theta, good news. That's the same theta from before, so we like to think of that as defining a half plane. Little terminology. I like to think of this half plane kind of like that half plane, kind of like this half plane, as being. Think of this as a bunch of doors, or basically a door that kind of swings around the z-axis. And in that sense, the hinges on the door are sort of like that as theta increases and that door kind of swings around. So I call this a half plane hinged on the z-axis. That's, I don't know, this might be another one of these terms of my own creation. Anyway, I like it. You're going to hear me saying that a lot. That's what I mean when I say that. Okay. All right, so theta, let me just clean up my mess. Theta defines effectively what I'm going to call the theta half plane. Okay, next. Phi, lowercase Greek letter phi, measures an angle measured off of the positive part of the z-axis. Very importantly, there's different directions that you can go off of the positive part of the z-axis. Specifically, phi goes toward the theta half plane. So positive values of phi go that way. And as you could probably guess, negative values of phi go backwards, away from the theta half plane. Is that cool? Is everybody happy? Yes?
For theta, is it always from the x-axis?
Yeah, that's right. Theta is always measured from the positive part of the x-axis and measured counterclockwise as seen from above. Yeah, yes.
Earlier you said that cylindrical chords were polar chords in 3 dimensions.
Yeah.
Is this also?
I hear you. A lot of students like to think of this as being polar in 3 space, but if we're going to use the term polar in 3 space, it can't mean 2 different coordinate systems. And frankly, this has less in common with polar than this does. So if you're going to use the term, I think it sort of has to be for cylindrical and therefore can't be for spherical. Does that make sense? I mean, I don't see any way to sort of justify using that term with spherical but not cylindrical.
Right.
So yeah, I don't care for it in this context. Yeah. Okay. All right. Okay, so we have theta, we have phi. Notice that between the two of them, that defines a direction, right? And once you have a direction, if you want to describe a point that is somewhat in that direction, all you got to do is tell me how far to go in that direction. And again, I'm kind of abusing the term how far. Again, technically, how far means a distance. Distances have to be positive. Rho is a coordinate, not a distance. It does not have to be positive. So I have to put the quotes around when I say how far. And I just find it very satisfying, and yet, of course, it's a little wrong. So anyway, be careful with that little point. But of course, if it is negative, if you're looking at a negative rho, then you just go the other way. Exactly as you would think. I hope. Everybody happy? Okay. All right. So that's spherical coordinates. Really, really useful in a lot of contexts. Now, how do we do conversion formulas? I'm going to draw your attention to this right triangle right there. Awkwardly, this right triangle, that little right angle right there doesn't look like a right angle as I have it drawn in the picture because of perspective and stuff, right? So that's just annoying. I find that, I don't know, I find that bugs me. Right? So what I like to do, and you don't have to do this, but I think it's useful, is I like to redraw that triangle looking sort of straight at it, just to avoid that little perspective problem. You don't have to do that, but I find it satisfying myself. Okay, so being as that is a right triangle, notice R, the cylindrical coordinate R, is one of the legs of this triangle. Notice that Z, the cylindrical coordinate Z, is the other leg of that triangle, and easy trig, Z is rho cosine phi, and R is rho sine phi. Just a little bit of geometry, a little bit of trig, looking at this triangle. Oh, whoops! If I can get this thing to come on, man. Oh, okay, there we go. Yeah, easy trig. The reason I like to point out this little bit of trig is because, as it turns out, this is really all you need to know in order to be able to make sense out of the conversion formulas from spherical to rectangular. As follows, we already know that x and y are r cosine theta and r sine theta. So knowing what r is, we're done. X and y, boom, there they are. Right? Z, boom, we already solved for it. I don't have to plug it into anything. It's already done. And so notice I get my full conversion formulas from spherical to rectangular just by observing these two formulas, green and blue, which are just nothing more than the trig of this easy little triangle. Okay. Now, for your consideration, you do need to know these formulas. These formulas here are very, very useful. This is required. You got to know them. That's an expectation. I've used spherical coordinates a bazillion times. They're bonkers useful. And yet I have never memorized these formulas. And I have no intention ever to memorize these formulas. The reason I don't memorize them is because I don't need to. Because this is something I can see effortlessly. I mean, easy trig, right? And then likewise, this, easy trig. And if you just understand this triangle and the easy trig of that triangle, the formulas fall out immediately into your lap. So for me, and everybody's different. That's fine, right? But for me, I will never memorize these. I rederive these formulas every time I need them because it's so easy to rederive. Everybody happy with that? You do whatever you want, of course, right? But if you, I'm just going to warn you, if you try to just straight up memorize these only, I predict, based on having graded a ton of papers, right, of Math219, Math212 students, you're going to get the phi and the theta backwards, right? Or you're going to get the sine and the cosine backwards here, or something. You're going to get it wrong at some point. It's just too easy to accidentally get it wrong. If you understand the trig, you can't get it wrong. Okay. All right. Moving along. A couple of quick examples. Here is a convenient relationship to notice between x, y, z, and rho. Think of that in a couple different ways. I think maybe the easiest is that if you have a vector with coordinates x, y, z, then the magnitude squared is rho squared. So, easy little conclusion. And so that, combined with this, allows you to realize that this will always be a sphere. Aside from the obvious geometric, again, geometrically this just says distance from the origin is a constant. Of course that's going to give you a sphere, right? But it also very immediately gives you x squared plus y squared plus z squared is c squared, which we recognize from high school algebra. That's being a sphere. Okay. So again, that's why they call this spherical coordinates, is because it's so easily connected to spheres. Now, an example that has a bunch of details to it. A lot of tedium in this. I'm not going to do the whole example. I'm going to leave about half of it for y'all to do for yourselves. By the way, I'm just noticing, it's just me or is it really hot in here?
Oh, yeah.
Yeah.
Okay. I see that there's a thermostat right there. Can you tinker with that maybe and see if, is there a little dial somewhere on the side maybe? Or I don't know. They may have it disabled.
It might be a building issue. BioSci 111 was also really hot.
Oh, is that right? Okay. Well, anyway, I will deal with it. I'm sorry? I see. Okay. I'm sorry?
I think it's just really hot outside today, and they still have the heat on because it's winter.
Oh my God! Somebody needs to fry for that. I'm up here doing aerobics, and I'm sweating like a pig. Okay. Anyway, so back to the example. So when you want to take a point in rectangular coordinates, such as this one, notice we can interpret those points like so. And if you want to find the spherical coordinates for this point, now remember when we were doing polar coordinates, there's kind of two different ways to write a point in polar coordinates, right? There's what I'm going to call sort of the right way and the wrong way. Right? They're both right. But there's the one where theta points you in the right direction and r is positive, and then there's the one where theta points you exactly the wrong way and you fix it by using a negative value of r. So, well, whenever you have an angle, the angle can either point you exactly the right way or exactly the wrong way. Spherical coordinates has two angles, and therefore we are going to find 4 different ways to write a given point in spherical coordinates. Now I'm going to walk you through 2 of the 4, and I'm going to leave it as a suggested exercise for you all to think through the other 2. I'm going to do the hard 2, leave you all the easy 2. Okay, so first of all, this point and the various different, you see various triangles in that picture, and it's pretty straightforward to persuade yourself that's pi over 3, and that this is pi over 4. Make sure you can do that trig/geometry, not that much to it there. And having noticed this, now let's begin the game of what choices do we have for our angles. The obvious first choice for theta would be that angle, which is pi over 3, previously noted. Cool. That's the easy one to work with. This is the one I'm going to leave for y'all to work out the details of, so I'm going to sort of set that aside. I'm going to notice that you can add pi. That means go around sort of a half turn, thus giving you your other option for theta, which is what I'm going to call kind of the, like I say, sort of the wrong one, sort of the backwards one. This value of theta back there. And again, keeping in mind, I'm interested in this point here. Okay, so let's think through now. How do we take this choice of theta and how do we flesh out some phis and rhos to make some spherical coordinates? Yeah. Okay, so starting off with what I'm going to call the I don't know. To me, the first one I'm going to do is the most geometrically natural one, and that is to realize, look, this is the angle that I want. That's the direction I want to go. And what is that value of phi? And there's a temptation to call it pi over 4 because, after all, we see pi over 4 right there. Again, you have to keep in mind there's a difference between how big is an angle versus what is the coordinate. Coordinates can be negative. And in this case, keep in mind positive values of phi go into the theta half plane. So that's the positive direction for phi. That's not the way we want to go per the observation I made here. So in fact, this value of phi here is negative pi over 4. Does that make sense to everybody? Okay. So 4 pi over 3 for theta gives us that blue half plane. Negative pi over 4 gives me this green sort of direction there. And between the two of them, those define that direction. And so now we're left with, as previously noted, how far do we have to go in that direction? Well, we just need to go this far. So, look at the picture and do the geometry. And I believe 2 square root of 2 is what that row will be. Everybody happy? All right, let's do the other one now. Okay, so back to the previous picture. We've already agreed we're looking at this value of theta, 4 pi over 3. Oh, yeah, question.
Sorry, what was
Yeah.
rho again?
Rho is going to be positive because the direction was in the right direction, right? And it's this hypotenuse of this triangle, so it's 2 square root of 2.
Right.
Yeah. Okay, so again with the theta, 4 pi over 3. The other way that I can get to a point that's in that direction is to go the wrong direction. So now let's ask the question, can I get to that direction, the exact wrong direction? Can I get to that exact wrong direction by angling forward in the theta direction? And yeah, that's actually not a problem at all. Keep in mind that the theta half plane, right, extends all the way down, and phi is measured off of the vertical. And there you go. That, right, it's weird to draw, right? But that's the positive value of phi that would get us going exactly the wrong way, which therefore would allow me to go backwards with a negative rho to get me to the point in question. So let's talk about what this green angle is. How much is that green angle? Well, don't forget, we've already agreed that angle is pi over 4. So pi over 4 plus my green phi that I'm looking for is pi. So that green phi is 3 pi over 4. Does that make sense? It's weird geometry. I know it's hard to look at and make sense out of. So this is a good thing to stare at and try to look at it from different angles. Draw your own version of the picture and think it through until it kind of gels in your mind. Yeah.
So we add the pi to the negative one that we got, not the original pi over 4.
Yeah, that's one way to think about it. Yeah, sure. Yeah, let me try to represent that in the picture here, just to clean up. Yeah, it's like I had a negative pi over 4 to which I added a pi. Oh, whoa, that's not right. To which I added a pi to result in 3 pi over 4. Yeah, sure. Okay, so there's that. Think through the other two. Again, I've noticed I'm leaving for y'all the pi over 3, right? So this is the pi over 3 option. Think through, there's 2 different values of phi that you could attach to this value of theta that would get you to this point. One with a positive rho, one with a negative rho. Good details to think through. Okay, moving along. There's a really nice application here on the next page relating spherical coordinates to longitude and latitude. If you set up the Earth as a sphere centered at the origin, North Pole on the positive part of the z-axis, equator in the xy plane, prime meridian in the direction of the x-axis. It's kind of the most convenient way to set up the Earth on the axis system. If you set it up like that, then notice east longitude is exactly theta. It's kind of awesome. The other map coordinate, north latitude, is not exactly equal to phi. Phi is measured off of the North Pole. It's not measured off of the equator, right? So phi and north latitude are different, but you can see that they always add up to a right angle, aka pi over 2, and therefore north latitude and phi also easily related by that formula right there. Yeah.
Can you go over one more time how you determine the direction of phi?
How I determine what now?
Determine the direction of phi.
Yeah, so phi is always measured as an angle off of the z-axis, off of the positive part of the z-axis, tilting toward the theta direction. right? So if I've already decided that theta is this angle, then I don't measure phi that way or this way, right? I measure the phi toward that theta direction. Yeah. All right. Okay, so easy relationships there. Another little nice, quick, easy observation is that rho, for any point on the surface of the Earth, its distance to the center of the Earth is the radius of the Earth. So that's a nice little freebie, as a little under 4,000, plus or minus, depending on your latitude. Actually, I don't know if y'all have heard this before, but the Earth is a little bit wider at the equator than it is at the poles, because of centrifugal force. It's kind of cool. Yeah. Anyway, for these purposes, close enough. Call it a constant. The reason this is valuable is because this allows me to turn map coordinates into spherical coordinates. And that's valuable because of, for example, the following question. A surprisingly simple seeming question that's actually surprisingly complicated if you don't make the right insight. And that is, given 2 points on the surface of the Earth, Durham and Oslo, let's say. How far is that? Yeah, it seems like it ought to be an easy question. It's not, if you don't make the right insights. Right? It's surprisingly difficult. So in particular, it's tempting to say, okay, well, we'll just measure the distance like this. Well, if you're going to actually build that tunnel, then okay, but you're going to have to figure out how to deal with the magma problem, right? So I don't think that's very doable. So practically speaking, such as if you're flying a plane, right, which, again, we burn massive amounts of jet fuel flying thousands and thousands of flights every day. You always want to do the shortest possible path. Figuring out that distance is really valuable. So here's the way you do it. Real clever. The locations have map coordinates. Longitude and latitude, well known, easily determined. Per above, you can write those in spherical coordinates. Nothing to it. The formula's on the top of this page. From the previous page, you can turn those into rectangular coordinates. Once you know the rectangular coordinates, keep in mind that means that I know the rectangular coordinates of these two position vectors, which makes it super easy to compute that dot product. Easy, this times that, plus that times that, plus that times that, nothing to it. Once you know the dot product, well, here's another thing I know about dot products. Dot products are, let's see here, I'll use the highlighter, the magnitude of the one vector times the magnitude of the other vector. So that just gives me r squared. And then times the cosine of this central angle that I'm going to call alpha. So easy formula to write down there. Now keep in mind, I know the longitudes and latitudes, and therefore the dot product. And I know the radius, so I can solve for alpha. And once you know that alpha angle, it's really kind of all over but the shouting. Because that central angle alpha and the distance that I'm actually trying to solve are easily related by way of this old formula from high school geometry. And we win. We computed that distance without any, we don't have to use any differential geometry here or anything, hardcore, heavy machinery. Just a couple of clever observations. Everybody happy? Yeah.
Is there a way to find that distance using just polar coordinates, or do you kind of have to convert it?
Well, you're going to need to know. You're going to need to get the rectangular coordinates, and this is three-dimensional, right? So you're going to need to know if you give me I guess you probably meant cylindrical. Cylindrical coordinates. If you give me the r and the theta, then that can give me a z. I think the first thing I would do is convert into spherical, and then convert into rectangular. Yeah. But you do need full descriptions of the locations. Yeah. Right. Okay. Alrighty, so moving along. Another conversion. This is just like it was in polar. We'll be super quick with this. If you have a rectangular equation and you want to convert that into a spherical equation, you pretty much just plug in. So x, we have a pat formula for x. Just toss it right on in there. And that said, I do think it's a worthwhile convenience to multiply out your square first. You multiply out that square first, and that allows you the opportunity to save yourself some heavy lifting there. I mean, so here I just saved myself multiple uses of the Pythagorean identity. Right? So, be on the lookout for little conveniences like that. Okay. Oh, and I think I see the clock, and I'm out of time. Let me make one little super quick thing here. Basically, you don't need to know this whole section about standard basis vectors. You do, of course, know the rectangular standard basis vectors. All this stuff is just an analog. I'm just going to point out super quickly that this is the vector where r is increasing and theta is constant. It's totally analogous to a rectangular standard basis vector. And you can write corresponding formulas, and you don't need to know them. We're not going to use them in this course. See you later. Have a good one.
Hey, boss.
Yeah, what's up?
Sorry, I walked in at 20.
Oh, yeah, no problem. Here, let me pause the recording here, and we'll get that noted.